Uh, is my screen visible to all of you?
Yes, it is.
Okay. So, hello everyone. Today I'm going to present our recent work in which we studied the evolution of the thermodynamic properties of a coronal mass ejection in the inner corona using COMP and KCO data. So let me first briefly introduce about the coronal mass ejection. So coronal mass ejection, as you all know, are the large structure of plasma with embedded magnetic field that are ejected from the solar atmosphere into the heliosphere, and they appear as a new discrete bright white light feature propagating outward in the chronographic field of view. And the image on the right hand side shows a classic three-part CME captured by Soho Lasco C2, and the three parts are leading edge, cavity, and core. Beside this, coronal mass ejection are the main drivers of space weather, so hence it is very crucial to study their evolution in the solar atmosphere. So now the question arises why we want to study the semi-thermodynamics. So semi-plasma may contain a range of plasma temperature ranging from cool chromospheric material to hot flare plasma. One such example is shown on this image, which is captured by Soho Lasco C2 on 8 November. And this is the location of the UVCS slit. And the color bar on the UVCS slit shows the Lyman alpha intensity on the left and log T on the right. And you can see that the different part of temperature of different part of CME ranges from log T 5.5 to 6.5. So as the CME propagates, several processes may occur that can exceed different form of energies like electromagnetic, kinetic, thermal, and potential, which can lead to CME plasma heating or cooling. So to understand these underlying processes, it is important to study their kinematics as well as their thermal evolution as they propagate in the solar atmosphere. And further, to provide this constraint on the semi model, which can further help us to improve our current ability of semi space weather forecasting. So now the next thing is why we are interested in the inner corona. So the semis have now been studied for several decades using white light chronography data, and it is well known that semi shows peculiar kinematics such as rapid expansion and impulsive acceleration in the inner corona. And it is believed that these changes are linked to three forces, which are Lorentz force, gravitational force, and drag force. But we still do not know what is the role of thermal pressure force in semi kinematics. So hence it is very important to study their evolution in the inner corona. Now, coming to the previous studies, this mostly study on semi-thermodynamics has been done using SOHO UVC's data at fixed heliocentric distance ranging from 1.5 to 10 arson. But although there are some studies using DM analysis on SDO AI data and Hinode AI's data below 1.5 solar radii, but in none of these studies, the continuous evolution of thermal properties of CMEs has been studied, and we still lack an understanding of CME thermodynamics in the inner corona. Fortunately, MLSO instrument K-Core COMP and UCOMP provides us an opportunity to study the CME thermal properties in the inner corona using multivalent data. So, motivated by this, we studied a thermal evolution of a CME that occurred on July 20, 2017 in the inner corona. And we have used data from MLSOK core, COMP, and SDOI data. So the animation on the right hand side shows this July 20, 2017 CME as observed by these three instruments. And you can see that a CME propagating outward in this K-core field of view. The yellow circle here shows the comp outer field of view, which is at 1.4 solar radii. And also, I want to point out here that when the observation of K-core and COM started on this day, this CME was already in the field of view. So only the core of this CME is visible in COM field of view. So from now onwards, we will be focusing on this analysis of this CME core only. And also, we have shown SDOAI 193 channel movie for comparison because 193 channel and COMP 1074 channel has similar temperature response function. And further, we selected a region of interest, which is shown by yellow rectangular box, which contain our CME core. And the zoom version of these region of interest is shown on the top right panel, where you can see that the CME core is propagating outward in this region of interest. Now, coming to the analysis, we have determined this plasma temperature using two methods. First is using a differential emission measure inversion technique on SDOAI data. For that, we have used DM inversion technique developed by Chang et al. We then created the EM map of this AI region of interest, and you can see that the emission measure of the CME core is mainly confined in log T 6.05 to 6.65, and then we calculated the total emission using this formula by adding the emission measure in all the temperature bins, and then EM weighted log T can be calculated by using this formula, which is given in Chang et al. 2015. So what we did that we chose four artificial slit on AI region of interest, such that they cover almost the entire CME core, and then we created intensity and EM weighted log T space time maps. We then visually track the CME core, which is shown by this blue dash curve, and the same dash curve is overplotted on log T maps, and we extract the value of EM weighted log T along this curve. Uh, so the bottom plot shows the variation of log T with along this curve, and which is shown by the green symbol, and the gray shaded region show the effective width of distribution in log T space, which is again given by this W square EM given in the Chang et al. 2015. So we can see that the CME core is maintaining a constant temperature of order of million Kelvin as it propagating in the AIA field of view. Second, Second, we have also determined the effective temperature from iron 13-1074 line width. So as you know that the spectral line width of any spectral line has contribution from Doppler broadening, non-thermal broadening, and instrumental broadening. And if we subtract the non-thermal and instrumental width from the total width, we are left with the thermal width. And the effective temperature can be obtained using this formula. So to obtain this non-thermal line width, we have used previously data of July 19, 2017, where there is no CME present in COM field of view. And we have used the method used by McIntosh and DuPont 2020 to calculate the non-thermal width, in which we subtract iron 13 line thermal width corresponding to its peak formation temperature, and the instrumental width of comb, which is calculated by given by Norton et al. 2015 from the total line width. So what we found that the non-thermal line width is not changing much with height. So we have used average value of non-thermal line width for our calculation. So again we placed the same four artificial slit on comb region of interest, and then created a space-time map of intensity and total line width. And we then extracted the line width along this curve, and then subtracted non-thermal and instrumental width to calculate the effective temperature. So and the plot here shows the variation of log T effective and EM weighted log T with height and time. The green symbol shows the EM weighted log T, and the blue cross symbol shows the log T effective obtained using iron 13 line width. So what we found that and the T effective and TEM are similar, show similar behavior within the error bar, and we conclude that the effective temperature measured using line width by taking into account the non-thermal broadening and the instrumental broadening is a good measure of semi-plasma temperature. And also we found that the temperature of the semi core is remaining almost constant as it propagates in outwards. So and that value of log T effective and log EM is found to be in this range. Now coming to the estimation of the electron density. So both COMB and UCOMB have iron 13 line, iron 13 1074 and 1079, which are density sensitive. So we can use their line ratio to calculate density in this from log T log row 7 to 10 range. But unfortunately iron 13 1079 observation was not available during our CME event, so we go for K-core polarized brightness data. So as you all know that the coronagraphy basically observe basically capture photospheric light scattered from this free electrons in the corona, and so the observed polarized brightness will depend on the column electron density along the coronagraphic line of sight. So and the transient events such as CME will cause an enhancement in density, or we can say intensity. So to calculate the excess polarized brightness due to CME, we subtracted a non-CME frame from all the CME frame, and then we calculated the column electron density using this formula, where PB is the excess observed polarized brightness due to the CME, and PB is the brightness of a single electron at a given angular distance. Which is the calculation of this is given in the Billings 1996. So we have used plane of sky assumption to calculate B theta, as our CME was a limb event, and this assumption is quite valid for our event. Then we calculated the CME electron density by dividing the column electron density by LCME, where LCME is the line of sight depth of the CME. So we then again created the density map of the core region of interest, and we then placed the same four slit on this region of interest and created column electron density space-time maps. And this dash curve is same as I have explained before, and we then extracted the value of column electron density along this dash curve, and then we divided it by LCME. So LCME we have calculated by fitting GCS motion fitting using two vantage by observation. One is K core, and then second is core 1A. I have not shown here the results because of the time constraint, but then after that we divided the column electron density with the LCME, and we found that this plot showed the variation of electron density with time or height. So we found that the CME core density is decreasing by a factor of 3.6 as it evolves, and the density decrease is also consistent with the CME core volume increase, which we again calculated using GCS fitted parameters. So, and the CME core density values has this CME core density has values in this range from 5.85 to 20.85 into 10 to the power 7 per centimeter cube. So coming to the summary and conclusion, so what we found that this CME is expanding and its density is decreasing, but it is maintaining a constant temperature as it traveling. So this means this CME core plasma must be heated as it propagates. But this extra heating source is still unknown. There are few studies in literature where they have discussed the candidate plasma heating mechanism, but there is still no widely accepted heating mechanism till now. And also we conclude that the expansion of this CME core behave more like an isothermal expansion than an adiabatic process during its evolution in the inner corona. And further, similar kind of analysis can be performed using K-core and UCOM data for extended field of view. And UCOM also has temperature and density sensitive line, so we can also obtain temperature and density using their line ratio, and we can test different diagnostic method. For example, for density we have two diagnostic methods. First is using K-core for polarized brightness data, and second is using iron 13 line ratio. Similarly, for temperature, we have thermal width of different spectral line, and we can also calculate temperature using line ratios of different spectral line. So this comparison of different diagnostic method has not been done in literature. So this can be performed. I think this is a very good way to compare different diagnostic method. And also our study demonstrated the diagnostic capability of Aditya L1, which is going to launch in 2nd September, which will perform on both spectroscopic and imaging of CME in the inner corona in 3 visible passband. In which one is continuum, which is centered at 1500 nanometer, and there are 2 emission line, and also in one infrared passband, which is similar to COMP and UCOM. Okay, thank you.
Okay, we have time for questions. Go ahead, Maurice.
I actually have 3 quick questions. One, I must have missed something really important because you were talking about a 2008 CME observed by SOHO UVCS, but then you jumped to
Yes.
the 2017. What's the connection between 2008 and 2017?
Okay, here I was just telling the importance of studying the CME thermodynamics. So here I was just giving an example that CME plasma temperature contain a range of plasma temperature, which is shown in this this is for this CME event. So I have used only for reference only.
Okay, just a reference. Okay, my second question is, later on in the talk, you mentioned the thermal widths and how it's 21 kilometers per second for the instrumental width of comp, but it's also the non-thermal magnetic or non-thermal width plots that you were showing later on.
Yes.
The non-thermal width that you deduced is 20, that sentence right there, 21 kilometers per second, but the instrumental width of comp, as you stated, is also, do you feel like that's strange or common? Is that common? I've never studied comp. I'm only studying UComp. Like, why are those the exact same numbers, or is that just a coincidence?
No, they should not. I mean, it's not like that. They should be same. I think it is for only for comp. They are same, and only for this spectral line, iron 13 spectral line, 1074 spectral line.
Okay, my third question is with Aditya being like you said, sort of a comp or UComp in space. Yesterday we were talking about cameras, a choice of camera, a choice of integration time, exposure time. How do you or your colleagues feel about your choice of camera? Is it? I assume it's not the same. You're in space, so how do you compare your camera and the quantum? Because you even showed in your last slide that you're going to try and look at the 500 nanometer, 530 nanometer green line. But our camera, our quantum efficiency is terrible at the green line, which is why we took out that filter. So what special camera do you all have $10 million or something? Like,
Multiple cameras.
oh, multiple cameras. Okay.
I think the instrument is a spectrograph based. It's not a imaging spectrum.
Oh, there won't be any coronal maps.
Different channels, so they may have different.
Yeah.
Please go ahead and answer. Sorry.
It says both spectroscopy and imaging.
Yes.
CME.
Yes. Yeah.
So
Jyoti, should I chip in?
Yeah.
Okay. Yeah, this is Dipankar here. So as I think Steve was pointing it out, so it has a spectrograph. So it has 4 cameras. Okay. So after the M2, the light beam is going to be splitted. One goes to the continuum, and the rest goes to a grating, and then you have dispersion, and you have 3 different pre-filters also. In addition, actually, we have multi-slit as well. So this multi-slit spectroscopy allows you to do, scanning, and then you make a 2D map. But we won't have a map as comp produces. So these are traditional slit spectroscopy, but with multiple slit spectroscopy. So
and multiple cameras, you said as well.
There are
right?
multiple cameras as well. So since you asked about the cameras, so the optical channels have a scientific CMOS cameras, 2K by 2.6K kind of dimension. These are very fast cameras. In fact, we have problems with the exposure time. We have to probably give 5 to 10 millisecond kind of exposure because the signals are pretty good. And unfortunately, the infrared detector is not as good as we would have liked. As you know, it was hard to get an infrared detector in India, so we could manage to only get a 512 by 512. So that really limits the 10747 spatial resolutions. And although the flux and the efficiency is not that bad, but it will take much longer to get a sort of map.
All right, thank you. That answers my 3 questions.
Questions, anyone? Okay, let's thank Jyoti again.